You ever have one of those project ideas that needs to grab a ton of data, like really, really fast? Well, today we're going to go on a little quest to build a high-performance data logger, and it's all inspired by a real-world problem someone was trying to solve. Let's dive in.
So check this out. It all starts with this fantastic question from a student engineer over on Reddit. They need to grab data from a whole bunch of sensors on their team's race car, log it all, and then get this, create a live display on a tablet. This is such a classic engineering problem, and it's the perfect setup for our journey.
All right, so the mission is clear. We need a system that can juggle a bunch of different sensors. We're talking thermocouples, potentiometers, you name it. And not just read them, but process all that data and display it in real time. This is really the heart and soul of so many modern electronics projects, whether you're building something for a science fair or for industrial monitoring.
So the first big decision is the platform. Now, an Arduino is an amazing little microcontroller, but for what we need, it has a big weakness. Its storage is super limited. If you want to log a lot of data or run a fancy display, you're going to need extra shields and more hardware. The Raspberry Pi, on the other hand, well, that's a full-on microcomputer. It's got the muscle to handle complex data, networking, and a display, all by itself.
Yeah, for this quest, the Raspberry Pi is our clear champion. It's not just a little controller, it's the brains of the whole operation. Because it runs a full operating system like Linux, we can write complex Python scripts, manage files easily, and shoot data over Wi-Fi or Bluetooth, exactly what that student engineer needed.
But every hero has a weakness, right? The Raspberry Pi, for all its digital smarts, has one major blind spot. It can't read analog signals on its own. See, sensors like potentiometers or many temperature sensors don't speak in neat little ones and zeros. They speak in a continuous range of voltages. So how do we bridge that gap?
And this is our first real hurdle. We've got to find a translator, something that can convert the language of the analog world into the digital language the Raspberry Pi speaks. Luckily for us, there's a tool made for this exact job.
And here it is, the analog to digital converter, or ADC for short. This little chip is our essential translator. It takes a look at a real-world voltage and just converts it into a number the Pi can understand. This is the absolute key to letting our super digital Pi listen in on the analog world.
Now you've got a few popular options. The MCP3008 is a great place to start. It's got 10-bit resolution. But if you need more precision, you can step up to something like the ADS1115 with 16-bit resolution. Think of it like this. A 10-bit ADC is like a ruler with millimeter marks. But a 16-bit ADC, that's like a ruler with micrometer marks. It just lets you see much, much smaller changes.
Okay, so we've got our brain, the Pi, and we've got our translator, the ADC. Perfect. But how do we physically connect them so they can actually have a conversation? Well, that brings us to our next step, picking the right language or protocol for them to use.
The Raspberry Pi has two main ways it talks to other hardware like our ADC. They're called SPI and I2C. You can think of them as two completely different styles of communication. And for a high-speed project like ours, choosing the right one is absolutely critical.
Let's just look at the differences here. I2C is great. It only uses 2 wires, but it's kind of like a walkie-talkie. Only one device can talk at a time. SPI, on the other hand, is like a full-on telephone call. It can send and receive data at the exact same time, which, as you can imagine, makes it way, way faster.
I know this looks kind of complicated, but this is literally a picture of SPI in action. Every one of those sharp little up and down lines is a bit of data zipping back and forth. And the speed is just incredible. We're talking up to 45,000 samples per second. That's fast enough to actually capture the tiny vibrations in an engine or the exact moment of an impact. So for our quest for a truly high-speed data logger, there's just no contest. SPI is the undisputed winner. That raw speed means we won't miss a single data point, no matter how fast things are changing.
Okay, we are so close. We've chosen our champion, we've bridged the analog gap, we've picked our communication protocol, but before we plug in a single wire, we have to cover the final, most critical piece of wisdom: how to not destroy your Raspberry Pi.
Please memorize this number, 3.3 volts. This is the golden rule. The Raspberry Pi's GPIO pins run on 3.3 volts, and they are not 5-volt tolerant. If you connect a 5-volt signal to one of those input pins, poof, that's it. It's one of the fastest ways to kill your board for good.
And it's not just the voltage. You've got to watch the current too. Any single GPIO pin can safely give you about 16 milliamps. But here's the kicker. The total current from all the pins combined can't go over 50 milliamps. If you pull too much, you can cause some serious damage.
So how do you stay safe? It's actually super simple. Just 3 steps. 1. Always, always, always double-check your voltages. Nothing over 3.3 V on an input. 2. Use a current-limiting resistor with things like LEDs. It's a tiny component that makes a huge difference. And 3. If you want to control something beefy, like a motor, don't hook it up directly. Use a transistor or a relay to isolate it from the Pi's delicate pins.
Yep, this is pretty much the Hall of Fame for fried pies. Mixing up the 5-volt and 3.3-volt pins, forgetting that one little resistor for an LED, trying to power a motor straight from the board, these are all super common and very costly mistakes. Trust me, it's way better to learn this stuff now than to learn it the hard way.
And that's our quest. We picked the powerful Raspberry Pi, we gave it an ADC so it could understand analog sensors, and we chose the super fast SPI protocol to get the data. And most importantly, we learned how to keep it all safe. You now have the complete blueprint to build your own amazing high-speed data logger. So the only question left is, what are you going to build?